Welcome to Chapter 17. We're going to be talking about electrical energy and current. So our first section here is about electric potential, and this is actually video A. And we are only covering certain parts of this, so it's important to note that we're not covering the bottom of 597 and 598 because we're only talking about uniform electric fields. So what we're going to do in this video is we're going to distinguish between these three things: electric potential energy, electric potential, and potential difference. Then we're going to describe the energy conversions that happen in a battery. So because there are forces involved with charges, right? Remember, a positive charge can be attracted to a negative charge, okay? Because there's the force, we can actually have electrical potential energy in a similar way to how we have gravitational potential energy. Right, so if you have a mass on Earth, right, the mass is attracted to the Earth, and the Earth's attracted a little bit towards the mass, okay? And same here, right, this charge is going to move towards this one, and this one's going to be attracted towards that one a little bit too. So this is what allows us to have this potential energy. So electrical potential energy is defined as the energy associated with a particle compared to its location in an electric field. So remember, when we talk about an electric field, right, the further we get out, or the more space there are between the lines compared to when it's closer and they're closer, this is weaker and this is stronger. Okay, so that means when this charge is here, right, it's going to have a stronger force pushing it out, okay, than if that charge was out here. Okay, then it's going to have a weaker force. Okay, so it depends on this distance here, right, this distance between itself and the charge. Okay, and that's what's going to determine the strength of that electric field. So electrical potential energy, okay, is a type of mechanical energy like we've talked about before, okay, and it is a part of the law of conservation of energy. So before, if you remember, we had mechanical energy equals kinetic plus potential. And before we had gravity and elastic potential energy, but now we can add electric to this. And it's important to know that all of these are conserved. So I just want to take a minute to compare electrical potential energy and gravitational potential energy because they're going to be very similar, okay, in the idea. So the key to both of these together, right, is remembering that it depends on distance. Right? In gravity, it's the distance above Earth, right? In electrical potential energy, it will be, from the charge. Okay, so both of them have to do with distance, though. Okay, that's really important. Okay, so like the picture I drew, if you have the Earth here, right, or we have a charge here, this is a charge, this is Earth. Right, it just depends on where our particle is, okay, and the distance between that and the object. And this happens because it's a force acting at a distance still, so we can get that potential energy because it could move, right? This one could, if it's, let's see here, if it's negative, right, it's going to move this way, okay, or if it's positive, it might move the other way, but it has the potential, right, the potential to move. Okay, and that's why they're both types of potential energy. Okay, so as we discuss this now, a small round charge, right, has an electric field that goes out in all directions from it, but this gets really complicated with calculating potential energy. So instead, what we're going to do is from now on, we'll only look at uniform electric fields, okay? Uniform electric fields. And uniform just means that the field is straight and has the same strength throughout. So it'd be like if we took a really long plate of positive charge on one side and a really long plate of negative charge on the other, okay? And then we drew our field lines, we'd get these nice straight lines, okay? I'm not perfect, but you can imagine these lines are just perfectly drawn, okay? The strength of our electric field is the same throughout. Okay, and when we're talking about it too, we're going to talk about charges are here in the middle, so we don't get any weird curving that happens on the corners. Okay, so this is an electric field. We can always assume that it's just straight now. So when we calculate the electric potential energy, okay, we are talking about it in a uniform field only. Okay, so this equation is only for a uniform field. We're not going to worry about anything else. And our equation actually might look a little bit similar, okay? So here we have the negative charge times the electric field times the distance it is traveling in that field, okay? So this does look a little bit similar, right, to mass times gravity times distance, except instead of mass, we have charge, right? And instead of gravity, we now have our electric field, and distance is the same. So it's still very similar to gravity, just like we showed with forces, okay? I also want to point out, here, let's make sure we're clear on this, right? So Q is our charge, right? E is our electric field. And D is the distance traveled. Okay, because this is still potential energy, we measure it the way we always did in joules, okay, which is that capital letter J. Okay. The reason it has this negative sign here is that negative sign just allows it to make sense because we have the two different charges with potential energy. Okay, so with a negative charge, you'll end up with a positive potential energy. With a positive charge, you end up with a negative. So it tells us whether it's gaining or losing potential energy accurately, depending on what kind of charge we have. Okay, so don't forget to use your signs here. This means something. Okay, and then your electric field can have a sign too, remember. So make sure you've got everything using the correct signs or you'll get the wrong answers. So now that we've talked about electrical potential energy, we're going to talk about something called electric potential. So I just want to make sure you see the difference. Down here, right, we've got this electric potential, okay, versus what we just talked about, which was electrical, I can't spell, sorry, electrical potential energy. So we had this added word energy, okay? So these are not the same. And you guys will have to make sure you know the difference between these two. Make sure you know the difference between electrical potential and electrical potential energy. So now, talking about electric potential, okay, the electrical potential energy, as we talked about it before, is useful, but it depends on the charge, right? So it depends on what charge is going on there, okay? But like when we talked about electric fields and we got rid of the charge so we could see the field created by one charge, now we're going to look at removing this charge again. It leaves us with a field that tells us the potential at any point instead of the field at any point. And this is what we call electric potential, and it uses the capital letter V. Okay, and because we're getting rid of the charge, we just take our potential energy and divide by Q. So they're very related things. But now we use the letter V, and this is without our charge that's moving inside the field. So the next step then is to take this one step further. So if you remember work is a force acting over a distance, right? We had work equals force times distance, okay? And so if we're moving charges around, the electric field is actually doing work, okay? Because it's pulling the charge closer or it's pushing it away. So work done on an electric charge in a field, causing a charge to move, okay, is called the potential difference. And we indicate that by using this delta in front of it because it's a difference. Remember, the delta equals final minus initial, right? So we're going to have V final minus V initial, okay? And don't focus on this too much, okay? And so then we get this equation here, okay? So our potential difference equals the change in potential energy divided by Q. So when we plug in for our potential energy the equation we just learned, okay, then we get the negative QED, right, divided by Q. Oops, I forgot my delta in front of it. Okay, then our charge will cancel out. And because the distance is really what's changing here, and that's the only thing that's changing, we can actually drop this delta symbol now. So this will end up simplifying into delta V equals negative ED. Okay, and it might help you remember that this is related to work. It's not actually work, but it's very connected. And so this form of the equation looks very similar to this one, right, where we had our distances, and in this case we have electric field instead of force. Okay. When we talk about potential difference, and when we talked about electrical potential in the the thing before, we measure it in the unit volts, okay? So it's spelled like that. It's named after a scientist whose last name was Volta, okay? And it's really important that this is a capital letter V, not a lowercase v, okay? So that is volts. So now I've introduced you to all of these different things that we are talking about with potential difference. One more thing I want to point out is how this potential difference looks in a uniform electric field, okay? So remember, you could have some charge here, okay? And if this is a positive charge, right, it's going to move in this electric field, and it might move this way until it gets here, okay? So it has moved. Okay, so that would be our distance that it has traveled, okay? And then we have the strength of our electric field. So as long as we know the value for this, we can always calculate the voltage difference or the potential difference across these two points. So when we talk about potential difference, right, we're talking about the difference between the voltage here and the voltage at this point, okay? And so that is the difference, the way it changes depending on that. Because eventually, right, if this charge kept going, it'd run into the end where it can't go anymore. So this all comes back to the idea of potential energy and that there's a possibility for it to move. But with electricity, we end up talking about this potential difference because it's a lot more useful information. So let's go ahead and take a look now at one of the ways that this is useful. So batteries are a really simple device that takes advantage of the potential difference, okay? So a battery is just a way to create an electric field that can move charges and do work, okay? And we know that batteries give us electricity. They run our cell phones, they operate our calculators, and a whole bunch of other things, okay? So when we talk about batteries, we discuss batteries in terms of the voltage, right? And you might recognize this first part here, the volt, which has to do with the potential difference. Okay, so this is essentially just the amount of work that a battery can do. So let's take a little look at this. Okay, so here I've got one battery, and a typical AA battery, AA battery, has a 1.5 volt difference. Okay, and batteries are made, they use chemicals to maintain or keep the same a potential difference across these terminals, right? So when you have it like this, what's happening inside the battery is there's a chemical reaction that causes all the electrons to move down to this side. So then when you take your battery and plug it into something and connect it, what this allows is all these negative electrons here, they all want to move through this wire so they can get to the positive side. Okay, so you've created an electric field in your device that essentially pulls the electrons around until they get to the other terminal of the battery. Okay, and batteries are designed so they can keep this up for a long time, and what happens when your battery is dead is that all the electrons that it can create has moved to the positive side, and it can no longer create this potential difference. So with this potential difference, I want to point out that just because I wrote 0 volts here and 1.5 volts here, doesn't mean it has to be that way, okay? Remember, we talk about a potential difference, okay? And that word difference is really key, okay? Because we don't have to set 0 here. 0 could be somewhere in the center, and this could be negative 0.75 volts, and this could be a positive 0.75 volts, right? But our difference is still 1.5 volts, okay? Or we could even have negative 0.5 volts here, and I'm going to write it a little lower, but a positive 1.0 volts here, and we still have a difference of 1.5, right? So no matter which way we do this, okay, the difference is 1.5 volts, okay? So we don't actually know what this is, and we don't really care. What we care is about the potential difference is this 1.5 volts that makes this battery work. So that brings us to the end of section 17.1a. In the next one, we'll actually practice some of these calculations, so you have some examples for that. So I know there will be a lot of questions about this section because I know it can be very confusing. So make sure you spend the time to think about this and have some questions ready for me when you come to class. I will see you guys there.